We can start in a few minutes. Michele, can you hear me?
Yes.
Okay, you can open the camera.
Okay.
Okay. Good afternoon to everybody. The title of the seminar today is Molecular Nanostructure on Ferromagnetic Metals for Spintronics, and it is presented by Dr. Michele Mattera. Michele Mattera obtained in 2017 his PhD in nanoscience and molecular nanotechnology from the University of Valencia, where he worked in Professor Eugenio Coronado's group in the field of molecular spintronics. Then he moved to the Parisian Institute of Molecular Chemistry at the Sorbonne University in Paris, where he joined the HIPOM team led by Professor Anna Prost in 2018. Later, he joined the polymers group led by Dr. Laurent Baudelier in the same institute. From October 2020, he joined the ChemiFlow group led by Professor Josep Puigmartí Ruiz at the University of Barcelona. His research background is in the field of material chemistry at the interface with the surface science, leading the development and study of materials of interest in the field of molecular spintronics. He also studied the controlled deposition of complexes formed by polyosometalates and functionalized phthalocyanines. At the moment, he is expanding his research field to the covalent organic framework and the layered double hydroxides in microfluidic domains. So, Michele, when you are ready, you can share your screen and start. The floor is yours.
So thank you, Sarah, for your kind invitation, and thank you everybody for assisting. I will now proceed to share the screen. So yes, you can start over. Can you see my screen?
Yes.
Okay. Okay, so briefly, this invited webinar will be, well, the title, as Sarah already have introduced, is Molecular Nanostructure on Ferromagnetic Metals for Spintronics, and it was part of my PhD thesis that was, then developed at the University of Valencia and the Material Science Institute. So I hope that with this seminar, I can convince you that, well, if you want to work with the surfaces, you can use a plethora of different techniques to then characterize the material you have formed on the surface. And also, well, if we can show some progresses and in the end to, well, to observe if this can be useful as for spintronics applications. So to start, this will be more or less the outline of this talk. So I will give a complete, I will try to be a wide introduction. I know that there are the audience is so wide, and well, maybe not all of you are familiar with this concept, but we will go step by step, and I hope that I can well, I can express clearly all the concept, and then all the concept that I have explained in section 1, then you will see how they will be used to then describe section 2, section 3, and section 4. And well, so we can start. So first of all, what is a self-assembled monolayer? So a self-assembled monolayer are spontaneous assemblies of monomers from solution or vapor that are absorbed onto a solution, and they form a nanometric thick protective layer. So these SAMS can be we can define 3 main regions. So starting from the bottom, we have the red region that is the anchoring group that depending on the surface we are going to work with, we can have standard groups such as carboxylics, phosphonics, or ester or silanes. Or in the case of metals, we can use sulfurs or selenium-based groups. For the body or the backbone, here we can find also we can find a different type of chemistry, but it can be well, fully linear chemistry, conjugated chains, branched chains, aromatic systems, more or less aromatic. And then in the final part, the heating group, the head, we can find, well, also all the chemical group that the organic chemistry can provide to us. So we can start with the simplest one, that is a methyl unit, so a CH3, and this can change also the properties of the new surfaces, or either we can have different functionality. So if for example we start with gold substrate, and then we want to make it more hydrophobic or more hydrophilic, we can couple a thiol to attach it on the base, and with a carboxylic acid, like for the case of the undecanoic acid, that can have a long alkylic chain, and then a short thiol group to be attached onto metal surfaces. Also, well, also as I have already introduced, depending on the type of anchoring group, we can also tune the interaction between the monolayer we are going on and the surface we are working with. And we can tune from covalent, purely covalent, polar, or to the extreme case of ionic interfaces. The body provides a well-defined nanometric thickness, and also it provides a packing structure and arrangement. And well, for the case of the heading functional group, as I also mentioned it before, we can we can tune then the surface of the new surface we are going to generate. We can tune the free energy, or we can tune its reactivity towards peculiar reaction, or maybe we can do a click reaction, for example. Then, in order to characterize all of these SAMS, there can be different methods. Simple, for example, starting from more simpler and easy techniques, like the wetting properties, using a contact angle goniometry, so we can have a direct idea of the hydrophilicity or hydrophobicity of the new surface. To have an idea of the topography, we can rely on microscopy techniques, atomic force microscopy, but also together with the scanning electron microscopy or transition electron microscopy, depending on which dimension we are going to watch, or including scanning tunnel microscopy. And then, well, we can also use more specific techniques like infrared base or Raman or XPS, or reflectometry or ellipsometry, if we want to evaluate the packing and the thickness of the layer we have formed. And these SAMS generally can also show a broad range of application as protective layers, or in molecular electronics, they can be used as dielectric because they can be either conductive or isolant or insulators. On electrochemistry, and also for biological and biochemical purposes, we can use it to stain or to study the addition of a certain molecule. And coming to the field, also they can find a use in the molecular spintronics. So coming to what is spintronics, or spin electronics is a relatively new field where the spin of the electron together with its charge is used to transfer and process information. So finally, it's the ability. So it's if we compare it with the standard electronics, where we mostly control the motion of the electron charges. In this case, in the presence of a magnetic field, we can control also the relative orientation of the spin, and this can help us to improve the speed of calculations, or also to be used as a qubit or for storage, because imagine you can store information in each spin orientation, like plus or minus s. The simplest spintronic device is formed by a ferromagnetic by two ferromagnetic electrodes separated by a spacer. For the ferromagnetic electrode, we can have also different materials. For example, we can have this perovskite, the lanthanum, strontium, manganite oxides, or transition metals such as cobalt, nickel, and iron, and their alloys. The spacer also can be either semiconductor or either insulating, and depending on the nature of this non-magnetic spacer, the device will be called spin valve or magnetic tunnel junction. How does it work? Imagine we have our ferromagnet. I colored. Imagine that we have two ferromagnets with two different, made of two different material, as you can see by the color code. If we apply an external bias and then we submerge this device into a magnetic field and we start sweeping the magnetic field, it's worth mentioning that a ferromagnet presence hysteresis in presence relaxation and hysteresis in the presence of an external magnetic field, and also it has a magnetic moment that can be aligned or in the presence of an external magnetic field, and the field needed to align it is called coercive field. So if we start sweeping the magnetic field and we reach and we start monitoring the resistance inside the current flow, in this case the resistance inside this type of device, we find ourselves in a situation of low resistance until we reach the first coercive field, where we align directly the first ferromagnet. And if we continue sweeping the magnetic field, we arrive to a state where this resistance returns to the original value. So it has a low resistance value, thanks to the fact that both ferromagnets, so that we, with the applied magnetic field, we reached or we saturated both coercive field, and we managed to align the magnetic moments with the respect of the external field applied. If we then go back, we do the same thing on the reverse, we will experience, when we reach the first coercive field, another high-speed state, so a resistance state, later followed by, when we saturate all this, when we overcome the coercive field of the second ferromagnet, again into a low resistance state. So we can define, and then if we cycle back, this cycle can be repeated several times. So with this, we can define two situations of resistance, taking into account that the lowest resistance is the resistance in the parallel, and the highest resistance is the anti-parallel configuration. And we can also define, the magnetoresistance, so the variation, the percentage of the magnetoresistance as the variation and the relationship with using these two resistance. Depending on the device we use, this effect will be called giant magnetoresistance or tunnel magnetoresistance. I comment this because in the 90s, giant magnetoresistance was used for the first time to achieve a high density hard disk, in this case 16 gigabyte, that until the moment was a breakthrough in the field, because, well, thanks to this head, they could observe a difference at least of 3 orders of magnitude between the low resistance and the high resistance states. In 2007, the first the scientists that first observed this effect were awarded with the Nobel Prize in physics. They also observed this effect around the end of the 70s. And in 2010, the technology finally produced the new type of random access memory based on the always on the TMR. But well, all these achievements were achieved using inorganic materials. But what happens if we want to move to the molecular world? So the first example where they first show a molecule, in this case it was the alku3, and the second one, well, they were reported at the beginning of the 2000, and well, they were observing that there were some promising results because organic materials can have a defined structure, are lightweight, flexible, and their property can be tuned at will by chemical synthesis. Moreover, they are less prone to depolarize the spin, so we can keep this effect also at higher temperature. And depending on thanks to the hybridization of the inorganic electrode with the organic part of the molecule, we can create a new kind of interface called spin interface that can be chemically engineered thanks to the chemical synthesis. And well, arriving to the point, have been some used in Spintronics. As we said, we can control directly the interaction between the monolayer and the surface. They can have defined diametric thickness. They can be modularable. And well, we can perform an active tuning and active control on this kind of interface. And if we go back, if we look at it in literature, we can find, well, when the moment this thesis was written, only 2 reports that showed some low and ambiguous values. So it didn't overcome the 16% at low temperature. And this could be due to the fact that there were some oxidation issues in this kind of electrodes. 10 years after, by changing to a less oxidizable electrode, in this case, this perovskite lanthanum strontium manganite oxide, this can be shown. So this shows a good result with high voltages and up to 2 volts for operating voltages, and then also they have reached almost 40% at 4K. So the problem with this material is that the Curie temperature of this material is well below the nitrogen boiling temperature. So it's around 50 Kelvin. So we cannot reach room temperature with this kind of configuration. So the motivation on this work is we want to obtain a working device at room temperature. But first, we have to start with the modification, the chemical modification of the bottom electrode or the ferromagnetic electrode with a SAM. And we wanted to do this with the cheap and easy applicable strategies in a chemistry lab. And we want to preserve the magnetic nature of the underlying substrate. And so we started working with cobalt and permalloy. These are our materials. So cobalt and permalloy. Permalloy is a nickel iron alloy made by 80% and 20%. Their Curie temperature is well far above room temperature, so they are magnetic at room temperature. They can they are already used in electronics, and so their transition to spintronics should occur easily. The problem is that they tend to oxidize when they are exposed to air. So in this case, I will first show you how we start, how we will use this oxide as growing platform for SAMS. In the second part, how we get rid of this oxide. And in the third part, a strange effect that we observed while developing the second part. So continuing, we can go. So we have an oxide layer. Oxide, we know that phosphonic acid can be characterized, can be grown. Phosphonic acid monolayers can be grown onto oxide surfaces. So we decide to work with this family of alkyl phosphonic acid of increasing chain length. And in our case, we first pretreated the sample, and then we had a reference, and then we measured the contact angle, because we know that this kind of sample of SAM should be more hydrophobic than the substrate itself. And then we characterize the topography by AFM. So we observe, just to remind you, this kind of SAM, it's very hydrophobic. So if we observe a contact angle above 100 degrees, we know that we have a high quality SAM. If the SAM is less than 90 degrees, it means that we have no SAM at all. So because our bare values are no treatment, 40 hydrogen plasma and hydrogen plasma, it make more hydrophilic at all. So 20 degrees, which was the lowest angle we could measure with our instrument. When we form the SAM, we see that we are well above 100. And also we can see a clear progression as we increase the chain length. So we observe that the hydrogen plasma promotes the formation of a high quality SAM. In order to study why this effect was due to the hydrogen plasma, we performed the XPS to observe how changing the oxygen peak when we do this kind of treatments. So at no treatment at all, we know that the bare material is oxide with also some OH. On the oxygen plasma, we increase the thickness of the oxide, but we reduce the OH density, while with the hydrogen plasma, we increase the OH density. And so this induces self-condensation when exposed towards the phosphonic acids. We also wanted to understand and also study the thickness of the oxide after these treatments. So we use X-ray reflectivity, which is a complementary technique to ellipsometry, and it can be used to model thickness and densities of the material. And also, as a qualitative point of view, by counting the number of fringes, we can have also an idea if we are changing, if we are increasing or decreasing the thickness of the material we are working with. So by AFM also we checked that the rugosity was not changing too much, and well, the thickness of the oxide also is not changing that much. When also we form the SAM, we also see almost no changes in topography. And also we don't observe an increase of the surface roughness. We also perform some kinetic, and so we saw that these SAMs can be formed in 3 hours, or well, maximum in 3 hours. Even though yes, after 1,000 seconds, we already have a quite stable surface. And for this kind of mechanism, for this kind of SAMs, 2 methods were described in literature. So uniform growth model, where you have a SAM that is first attached to it first reaches the substrate, the surface, and then it starts arranging until the final packing is achieved. And so until also the final thickness matches the theoretical one, or the Islam-like growth model. So where we have patches of the SAM that are formed, and then there is coalescence until the complete monolayer is formed. We observe in our case that we are in the uniform growth model because we don't observe any patch during this we did this kinetic study. By infrared, we can observe a qualitative information where we observe that, well, thanks to the shift in frequency of the CH2, we can attribute a more or less crystalline film. And quantitatively, also by studying the intensity of the CH2 and the intensity of the CH3 associated signal, we can also calculate the tilt angle. And we can see that what we observe qualitatively, we can get also quantitative information. Again, with X-ray reflectivity, we checked. And finally, we also checked by XPS. And we see that we have a good agreement with 3 different techniques. And well, it's we are sure that we could grow this sum. We also perform some magnetic measurement using magneto-optical Kerr effect, which is the an equivalent technique to squid, but it uses light in the presence of an external magnetic field and studies the changes of the polarization of the incident light in the presence of a magnetic field. And with this, we can reconstruct the magnetic hysteresis on the surface we are watching. We prepare different kind of samples, a standard, an oxidized, hydrogen treated, hydrogen plus some, and oxygen. And we can observe that there is a clear difference. So, we don't observe any difference between the hydrogen treated, plasma treated, and the hydrogen plus some. And when we then increase the quantity of oxide, we observe an increase in the coercive field, thanks to this is done because of the exchange bias between the bulk and the oxide. And so for this part, we can see that this activation is critical. The FM, it's the surface are smooth, and the high quality monolayer has been fully formed, and we don't observe any change in the magnetic properties. Then, in order to then graft it on the metallic part, there are different strategies that can be used. So if you possess a UHV facility or a clean room facility, you can follow path 1 or path 2. So without exposing, so in this case by sublimation, or in this case using a glove box, you can form an oxide-free substrate. But what we want to develop is more or less strategy 3. So where we can fabricate in some place of the world the surface. The surface is sent in air, so it can get oxidized. And what we want to observe is how we can get rid of this oxide without affecting the metallic bulk, grow the sum, and then finish the complete device. So in order to obtain this, we are looking for a candidate that can show selectivity compatible with the glove box. It should not increase the surface roughness, easy processability, easy implementation. And so in literature, all these characteristics are answered by the wet chemical etching. In this case, we perform the etching. We study the thickness by reflectivity as already introduced, and also we then take a look at the morphology of the structure of the surface. So if we if we take cobalt and we do our fit, and then we expose it to this glycolic acid for 26 minutes in air, we observe that all the fringes are gone. This is the characteristic signal of a silicon substrate with nothing on top. So we observe this, And then we started thinking what was happening. So in this case, we just, as I said, we exposed to air, we did a kinetic, and so we observed that over the course of 26 minutes, we were losing some material. This is the thickness from the adjustment of the XRR. In the approach B, we were using a glove box, and we saw that, yes, after a first jump, then we observed that this thickness is maintained. And then we started cycling between glove box air until the 26 minutes are reached. And in this case, we see a clear staircase behavior. So our hypothesis is that if we perform the etching in air, the glycolic acid attacks the oxide, the surface, the metallic surface reoxidizes, the glycolic continues attaching until all the substrate is etched, all the ferromagnetic material is etched. In the approach B, so in the glove box, we observe that, yes, the glycolic acid will attack the oxide, but since there is no more oxygen, we will not reobserve reoxidation, and so the glycolic acid is not touching the ferromagnet. And in this case, we have a selective oxide etching of the oxide. And also the roughness is maintained. We can see a clear surface after barely 50 minutes of exposure. We also did some tests. So we prepared some stamp using microfabrication techniques. And so then to be extremely sure that the glycolic acid was not touching in this case, the cobalt. And we observed that after the exposure, we didn't see, so yes, we see this 2 nanometer of thickness of the decrease, but then we don't see any other jump. And by XPS, we also wanted to study, so we have a reference sample, oxidized sample, and recovered sample. By XPS, we can observe that no oxygen is present in the reference value as also in the sample we exposed with the glycolic acid. And also we can see that the cobalt signal also corresponds to a metallic bulk. The magnetism also speaks clear. Then yes, we have the same hysteretic values, the same coercive field from the reference and the treated sample. And well, we also did the same thing on permalloy. Permalloy being formed by the mixture of these two metals, well, is less prone, is less reactive towards the glycolic acid. So instead of needing barely 20 minutes, it needs 16 hours. But we can also see that the same rules apply. And by XPS, we also observe the same. So we recover the metallic surface. So in this moment, we have a metallic, so we are in presence of a metallic surface. And from the introduction, you remember that I mentioned that thiols or sulfur-based are an exceptional bending layer for metallic, show very high affinity towards metals. And so, well, also we use the same analog family, this time changing from the phosphonic to the thiol group. And we started with this. So we prepared the solution, and after 50 minutes on top of the same solution, we added the thiol solution. And we measured the contact angle, and we observe that there is a difference. So we have a sum with the respect of the reference. Also, we did a study in time, and we see that, well, yes, the etching, once the etching is finished, the sum formation takes place. So first the approach and then the stabilization. Okay. And then we also have checked that if we prepared it, the surface is very smooth. The infrared shows the formation of the SAM, and also having done all this methodology, we have observed that we have did some SAS measurement, and we observed the presence of degrades at the room temperature. So this means that the full device is still ferromagnetic, or at least the bottom device that has been modified with a C12 dodecanothiol SAM is still ferromagnetic. We also tried this with the other families, and so we see a clear progression of the angles. And we also try to form the device. So in this case, it's a method developed in France, where they can, using a conductive tip IFM, they could do holes of a controlled dimension of 20 square nanometers by indenting this photoresist, and then we could grow the SAM, and they grew the SAM, and they have completed the cobalt, the top part with the cobalt. So they perform at room temperature. We have a nice IV curve, and also we observe a 60% of tunnel magnetoresistance at room temperature. Well, with not so high bias voltage, but at least, well, it's something. So this also is, it was done in collaboration with Sophie Delprat, and show this nice result in her thesis. So to conclude this part, we have observed this glycolic acid is effective etching agent. We can expose, and this surface is chemically active. The alkanethiolate SAM is growth, and we can implement it for spintronic application. But as I introduced before, so if we perform,
Michele, sorry for interruption.
yes?
You have at most 10 minutes.
10 minutes, okay, yes. Enough.
Okay.
Okay. So what we have observed until the moment, if we do this process in a glove box, the surface is smooth, but the moment we expose this substrate with this surface to the air, we observe lamellar domains. And first we started thinking about contaminations, then we checked everything twice. We checked the purity of the substrate, the purity of the solutions, and we were not capable of identifying the problem. Then we started studying with the AFM, and we observed that we have different tickets. Depending on the molecule, we can obtain different structures with also different morphologies. And we observe also that this we can observe it by eye with an optical microscope, and this structure presents some levels, some layers. So we went to the literature, and well, we observed that some lamellar material of transition metal based on transition metals were reported in literature as bulks or as a surface only in the case of silver. And so they were proposing that they had metal and then the broad alkyl chain, in this case coming from our SAM, that is extending on top and on above and below the metal sulfur plane. So how can we demonstrate it? We first start with the AFM. So we observe a certain periodicity depending on the molecule we were using, certain periodicity. We did some XRD. And also when we started fitting the data, we observed that all this info corresponded to the double of the thickness of the SAM we were using. And we also observed that this molecule can have, depending on the eye, we can have thicker molecules, thicker structure, or thinner structures. So We also have looked at the reported values. Our values agrees, and we observe that we imagine that the internal structure should be this one, that is adopted by LDH and transition metal decalcogenides. We also have observed that, well, some of the material will come from the surface, from the original SAM, and also we observe some interdigitation. So it means that we have something on the bottom and this is growing on the top. And also we observe that, well, shorter molecules tend to have a bigger area structures, while longer molecule, shorter area. With thanks to Raman, we have observed the presence of the alkyl chain only inside these lamellar structures. By Auger, we determine the presence of cobalt and sulfur, and so in this case, we could characterize this kind of structures. We also observe that they can grow over time, but to me, the most impacting is this one. So we also have not only by FM, we also observe it by eye, that over the course of 16 hours, plenty of this structure appears. It was very puzzling for us. And also, if you looked very close with the AFM, you could etch them layer by layer. So it was a tricky material to characterize, and so this is our mechanism. So an initial oxidation causes the migration and growth, and that's why we get a layered structure. So just to conclude, these domains appear when exposed to air. It doesn't. It doesn't need any external stimuli, and well, is the effect of the oxidation of the metal beneath the surface. And we imagine this is the internal structure, and we have proved that the chain length that the molecule we use to functionalize the surface can give us different lamellar structures. And so, just to conclude, we have reported in this paper the result showed in the first section. In the second paper, we have reported the use of glycolic acid, and in the third paper, we also reported this coordination polymer that will grow on functionalized ferromagnetic surfaces. So yes, thank you for your attention, and the floor is open for questions.
Thank you, Michele, for your very nice and interesting presentation, and for, of course, accepting my invitation today. And now it's time for questions. I remember you that you can write them in the chat and I can read them for you, or you can open the camera and ask directly. So, are there questions? Don't be shy. Okay, in the meantime, I can ask you just some curiosities. You talked about some applications, but are there more applications that are under investigation yet, or not?
Well, now they are, as far as I know, well, they have implemented some, they are developing some of this application for flexible electronic. So they have done Spintronics onto organic electronics. So it's a continuous evolving field. So I don't know if then it's Samsung or some Asia-based manufacturer that also is trying to develop and push this to the market. So yes, mobile or yes, small consumer IT.
Okay. We have a question from Professor Teti.
Yes, Michele, thank you. It has been really a great talk. I'm not expert in the field, but I think that I could follow well what you were saying. And my question is probably a naive question. If there is any application in the biological field, for instance, to investigate enzymes or molecular complexes in an artificial system that, however, would be much more controlled than in the biological.
Well, yes. Well, thank you for the question, and well, that was my hope that yes, it was easy to follow. So yes, SAMS, yes, they have been used to actually the SAMS are also used in the COVID test or in the pregnancy test. So as a fast application, because they can store the well, the phosphorescent or the fluorescent agent, and so that's why you can have a quick test using a very cheap fabrication method. And so yes, so then I think that there are also application with well, for cell staining, cell sorting, depending, and also yes, if we want to study certain type of cancer, I think they use SAMS to modify this well, the glass or the substrate they want to immobilize these cells to be studied.
So the principle is this one, the one that they use also in diagnostics, and so it's a huge field actually.
Yes.
I would say, especially when you need a fast and also easy way, for instance, to test some molecule or any type of changes, for instance, in biological fluids.
Mm-hmm. No, it's actually, yes, you can use some for fast screening. So if imagine I show you some pattern, but if you are capable of patterning different kind of analytes, or well, different kind of probes, then you can test in the same space for different cells, and so also you can save space, time, and well, in one shot, in one run, you can also have a quick response.
Thank you.
To you.
Okay, we have another question in the chat from Ramon. The question is, how easy is it to use this approach to coat particles, and which kind of applications can be achieved?
So, well, it's well, for when you pass from a surface and you shrink all the dimension down to nanoparticles, finally you have the well. In order to stabilize nanoparticles, you can have also colloidal stabilizing agents, so the surfactants. So finally, when you prepare a nanoparticle and then you use a surfactant to suspend, basically you are forming an ionic SAM. So it's already an application, Ramon.
Okay, we have another question from Luisa.
Well, thank you, Michele, for your presentation. I think it was very nice, very interesting. Also, that you show the characterization of these materials. I have a curiosity. If the presence of this island that you follow, even the kinetic deformation of this island, can affect the magnetic properties, the properties of the material, the potential application for spintronics, or it just different organization of the molecules of the material?
Well, we during the development of this work, we were also asked about this, and well, we were hoping at least that they could conduct electricity. So we did also some conductive AFM to characterize, but they were not showing conductivity. And the fact that they were growing at the benefit of the surrounding SAM, the problem is that then this surface is completely oxidized. So this
Can
is
use the
just to show
properties.
that yes, it's actually is, if you do something wrong, this you cannot use then in Spintronics. This was a pity.
It is difficult to. It is also difficult to control a
Yes.
process like this. It's just spontaneous, and so
Yes, because
maybe not reproducible.
well, in this case, we could reproduce this error,
Okay.
or but
Okay.
then we
But
could not we could not use in benefit of the spintronic application.
Okay.
Yes.
There is always a lot of work to do.
Yes.
This
And
is research.
there are always new ideas, always.
Yes, let's
Thank
hope
you.
so. Thank you for the presentation again.
Thank you, Luisa.
Are there more questions, curiosities? If not, I want to just to do a consideration. If you want to tell the audience something about the importance of nanometric dimensions on the properties of these systems.
Yes. So, well, when well, if we have to speak about this, we are a little bit moving out from the chemistry. We are entering more into the quantum physics, and so it's a very complex word. In order to develop this, I could have a little hint on which are the processes and which are what we have to think when you are working at this nanoscale. But as well, it's an interesting field for sure. And well, yes, as they say, the size matters. And for this kind of processes, if you really shrink down and you can arrive to the single molecule electronics, which is the limit and the dream of the founder of this field, maybe we can understand more things. And also, even if it is basic science or basic physics, it can be then used to develop new applications. So it's a field worth to study, I think.
Okay, thank you, Michele.
Thank you, Sarah.
Well, if there aren't more questions, I want to thank you. Okay, we have a message from Professor Teti. I like the term Spintronics, looks very dynamic. Congratulations, Michele.
Yes, exactly. It looks like you have to be pushed somewhere. Okay,
Yes.
and Sarah, I displayed in the chat also the link to for those who are interested to a position in our lab. So it's displayed in the TMS website and in many other websites around. Thank you.
Okay, thank you. So thank you another time, Michele, for this presentation today and for joining. And I want to present the seminar of next Thursday. The title is Clonal Expansion in Inflammatory Bowel Disease, Friend or Foe. The presenter will be Elisa Motin from Cancer Research UK Cambridge Institute. So thank you to all of you for joining today, and see you next Thursday.
Thank you.
Yeah,
See you.
bye.
Hello.